In this second example, we'll basically doing the same thing, but slightly more complicated. So it's Calc 1, with the idea, vary one parameter at a time, one variable object, Calc 1. Set up our integral inside the circle of radius 2 and above the line. Convert to polar coordinates. In the first equation I can solve for r, and in the second equation I'm also going to solve for r. How come I didn't solve for theta like I did in the last example? Let's draw the picture and all would become clear. There's my circle. There's my line. Region above it. There's the center of the circle. Going from this first theta, fix a theta. My radial lines are no longer going from the origin. They're going from the line to the circle. So I need r equals for my upper limit, and I need an r equals for my lower limit. Add all these thetas up. So I have my first theta where I start summing my lines, and I have my ending theta where I stop summing my lines. To find where that theta is, that's when my line squishes to a point. That's when my upper limit equals my lower limit. Now I can solve for theta. One slight problem, theta appears twice. So I need to convert to a form where theta appears once. So I use the addition formula, one of the 3 trig formulas you have to know. Theta twice. There's no way to solve by hand. Do the reduction. Theta is now once, easily solved by hand. To apply the formula, r sine theta is a 1, r cosine theta is a 1. I square and add. Sine squared plus cosine squared is 1. And so I get r is √2. Dividing them, tangent is 1. Plugging into the formula, theta appears once, and I solve. Arcsine 1/2 √2. Arcsine, of course, has 2 values. Principal value, inverse sine. And the symmetry value, pi minus inverse sine. The first value is where I begin, the second value is where I end. How do I know? Plug it in my calculator, see what the number is. Minus 0.43 radians, minus 24 degrees. That looks about right for the picture. 2 radians, 114 degrees. Looks about right in the picture. Without the picture, how would you know? No way to tell. Rewrite it in parametric form. X is r cosine, y is r sine, z is equal to 0. That's the equation for the surface. dA, r dr d theta. And I replace the variables with their parameterization. Let me just go and call these numbers theta 0 and theta naught, just for simplicity's sake. So I'm integrating from my lower limit up to my upper limit, summing over all the parameter values. Replace x, replace y, replace the differential. So this inside integral is my line integral. There's thetas in the limits, there's thetas inside it. It's all a function of theta. I could pull out the cosine theta, sine theta if I want. Clean up the algebra. Integrate in R. And plug in my limits. Plug in my upper limit. And I'll plug in my lower limit. Cosine theta, sine theta, times r to the fourth, 1/4. This is some nasty Calc 1 integral, and so we'll just call it done. The first piece I could integrate. Second piece is more problematic. I could probably do it if I hammered on it, but why? It's just sadness.